Video for the sequences and series test review. Let's jump on in with problem number 1 here. We need to express this multiplication in factorial form. And so 8 factorial would give us 8 times 7 times 6 times 5, but it would go all the way down to 1. That's the definition of 8 factorial. We needed to stop after 5. So we stop it after 5 by dividing away 4 factorial. That way, the 8 factorial will still include the times 4 times 3 times 2 times 1, but the 4 factorial will cancel out all of those terms, leaving from just the 8 down. Let's try that with this one over here. 122 factorial divided by 115 factorial. Don't make the mistake of doing 116 factorial, or you will cancel out this 116 here. All right, going the other direction, 130 factorial divided by 127 factorial. So it's going to be 130 times 129 times 128, but then we stop because everything after the 127, including the 127, is canceled by this 127 factorial. What's 5 factorial over 0 factorial? Well, that's 5 times 4 times 3 times 2 times 1, and 0 factorial by definition is a 1. So we can plug this into our calculator to solve it. 5 times 4 times 3 times 2 is 120. The ones don't affect the final answer. Final answer 120. This one here, we should actually go ahead and do that multiplication as well. 130 times 129 times 128. I get 2146560. So 2 million. Approximately. All right, state if a sequence is arithmetic. What we're looking for is how the sequence is changing, and specifically if we are adding or subtracting a constant amount. That's what would make it arithmetic. So how do I get from negative 40 to negative 34? Well, I've got to add 6. Let's see if adding 6 continues to work. It does, so this is yes. Yes, this is arithmetic. Now, in problem number 6, to get from 4 to 16 by adding, it would be a plus 12. Does plus 12 get us from 16 to 36? No, that's a plus 20. So something else is happening here. And it looks like, well, I'm not really sure. It's not times 4. It's something else, but it doesn't really matter. These numbers don't match, so we can just say no, not arithmetic. All right, so these next sequences are definitely arithmetic sequences. We're going to use that fact to go all the way out to the 52nd term. So first thing we need is the common difference. What are we adding or subtracting here? To get from 19 to 13, if I'm not sure, I could go backwards. 13 minus 19, I would get that this is a minus 6. So that's our D. All right. This is our first term here, 19, so this is our a sub 1. Then we use the formula that a sub n is equal to a sub 1 plus d times n minus 1. So you get to add the common difference n minus 1 times. So let's plug in everything we've got. Our initial term is 19 plus a negative 6 times 52 minus 1. Just going to plug that all into my calculator. 19 plus negative 6 parentheses. I'll just do a 51. I get negative 287. All right, common difference for number 8. Looks like we are subtracting 9 each time. I'll let you go ahead and figure out what the 52nd term for that one is. All right, rewrite each series as a sum. So we got to know how sigma notation works here. So what we do is we start plugging in the number we see at the bottom in for the variable, and then we keep adding 1 to that until we reach our stopping point, which is the number on top. So this is 4 to the 1 plus 4 to the 2 plus 4 to the 3 plus 4 to the 4 plus 4 to the 5, and then we stop because we reached 5 with what we were plugging in for A. All right, you can try that with number 10. All right, evaluate the series. So when we see series, you can think sum. So it means actually add the sequence, and that's what makes it a series. It is just one number. And these are arithmetic, so that's important for knowing what formula to pick. All right, so for number 11, we've got the first and the last term and how much we're incrementing by. So we can plug those into our formula, which, because this is arithmetic, we're going to just do our first plus our last. We want to add them, divide by 2 to get their average, and then we want to multiply by n. And we've got all of that information already given here, so let's just plug it in. -9 plus a -69 divided by 2 times 7. So that the average there, -9 plus -69 divided by 2 is 39. We have 7 instances, so -273 is what this evaluates to be. All right, same process for number 12, but 13 and 14 give us the information in a slightly different way. What we don't have is the last term, which is part of the formula. So we need to use our formula for the nth term to figure out what that last term is, so we can plug it into this formula. So a sub 14 here is going to be equal to our first term plus our common difference, which I see is 3, times the n minus 1. And let's see what that is. 10 plus 3 times 13 is 49. So I'm just going to write this as a sub n again, but it's our last term. It's going to be 49. So now we average the first and the last terms. 10 plus 49 divided by 2. We multiply by the number of numbers, which is 14. 10 plus 49 divided by 2 is 29.5. Times 14 gets us 413. All right, and maybe it's a good time to go double check our answer key. For 13, we got 413. And let's double check this one, -273. Yep, okay. On to some geometric series. So, how would I know if this sequence is geometric? Well, similar to an arithmetic sequence, which has a common difference, these have a common ratio, meaning that I'm multiplying by the same number each time. What do I multiply -3 by to get -18? I multiply it by a +6. If I multiply -18 by +6, do I get -108? Let's check that in our calculator. I do, and my guess is if I multiply by 6 again, I'm going to get that -648, so this is yes, geometric. This one here, well, I'm not entirely sure what I would multiply by, but I see it's a +1, +1, +1. That can't be geometric. That's arithmetic. So no, not geometric. Whatever I'm multiplying by is not staying the same. All right, so 17 and 18 are definitely geometric. Can we use that information to find the 8th term? So how we find the 8th term is you figure out what the common ratio is here. So it's a times 3. And then you do all of those times 3's first. So 3 to the 8th. And then you bring in our initial term, which is a 1. So 1 times 3 to the 8th. 3 to the 8th is 6,561. All right, same here. This would just be 4 to the 8th. 4 to the 8th. 65,536. And let's say it didn't start at 1, we would then take this and multiply it by the starting number we see there. But both of these start at 1. Probably should have made one of them start at something different. Oh well. All right. Evaluate the series described. So series, that makes you think of the word sum. That means we're going to write out the sequence and then add all of the terms together. So we're not going to really do that because we're going to use the formula, which is a sub 1 times 1 minus r to the n over 1 minus r. Make that look a little more like an n. All right, plug in what we've got here. So 1 times 1 minus 3 to the 8 divided by 1 minus 3. 1 minus 3 to the 8 is negative 6,560. Divide that by negative 2, and we get 3,280 for 19. 3,280. All right. So that formula is pretty easy to use. You can do it with number 20. Let's move on to number 21. We got a problem about money here. We're going to deposit $30 every day into an account that pays 1% interest every day. How much money do you have at the end of the year? Assume that the last payment gets to grow 1 time and the first gets to grow 365 times. So that last payment, we're going to start with the last payment first, is just a $30 that gets to be multiplied by 1.01 one time. We're then going to add that to the $30 we put in the day before, which gets to be multiplied by 1.01 2 times for the second to last day, and then again on the last day. This is going to go all the way up to the very first deposit we made, which was $30, which got to grow by 1.01 365 times. So this should look like a geometric sequence with our initial term being equal to whatever this is when we plug it in. So 30 times 1.01, it's 30.3. Our R value is 1.01, and our N value is 365. So let's put this into our formula. 30.3, 1 minus 1.01 to the power of 365, divided by 1 minus 1.01. Plug that into our calculator. 30.3 times, in parentheses, 1 minus 1.01 to the 365, close parentheses. Press enter, divided by negative 0.01. And we get a very big number. 111,453. So $110,000. 453. And we only deposited a little short of $11,000. So the whole rest of that is just interest that is really nicely added up. That, for example, that very last payment, the 1.01 to the 365, made that very first $30 37 times more valuable. Okay, let's look at 22 real quick. How much do I need to deposit each month into an account that gains 24% annual interest compounded monthly in order to have $4,000 at the end of 5 years or 60 months? So we want the final answer to be 4,000. Our initial value, it's going to be the amount we're depositing that's allowed to grow once. So we don't know what that deposit amount is, but if it grows once, let's see, 24% divided up amongst 12 months gets me 2% per month. So it is x times 1.02. And then the whole rest of this we know. The rate is that 1.02. It's not the full 24% because it's getting paid out monthly. So 2% every month. To the power of 60 pay periods divided by 1 minus 1.02. So this whole thing can be plugged into the calculator. 1 minus 1.02 to the power of 60. Press enter, divide by negative 0.02. I get 114. So 4,000 equals x times 1.02 times 114.05. Let me add in that 1.02 by multiplying that in. We get 116. And I'm going to divide both sides by 116 to get that 4,000 divided by second answer equals $34. And we're going to round this up to 39 cents. We always want to round these up so that we get at least the 4,000. If you round it down, even if it looks like you're supposed to round down, you'll end up with just under $4,000. Okay. A little bit binomial expansions. So let's see, we'll do the one that's bigger to the fourth here. The first term, well, actually this one's going to be harder because it's the second term. So with the second term, my coefficient, I need to go to the third row of Pascal's triangle. So that is the row that goes 1, 3, 3, 1. The coefficient of the second term is a 3. And then a went from a to the third to a squared. And then b went from no b's to b. And then this is going to fill in for a, this is going to fill in for b. So 3 times u squared times negative 5, which equals negative 15u squared. Negative 15u squared for 23. Let's see if we got that right. Yep. Okay, maybe that'll make more sense when we expand number 25 completely. So this is a to the third. So I get my coefficients from that third row of Pascal's triangle. Let me actually space out even more. 1, 3, 3, 1. And then the variables go a cubed, a squared, a, no a's, and then no b's, b, b squared, b cubed. All right, and then we're going to plug in a y for a and a negative 2 for b. So y cubed plus 3 times y squared times negative 2 plus 3 times y times negative 2 squared plus negative 2 to the third, y cubed minus 6y squared. Let's see, that becomes a 4, so plus 12y, and that becomes a minus 8. Is that completely expanded using our binomial expansion theorem. All right, what is the 35th triangle number? So that is 1 plus 2 plus 3 plus 4 dot 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 plus 35. We figured that out with our sum of an arithmetic sequence formula, so 1 plus 35 divided by 2 times 35. Plug that into our calculator, so 36 divided by 2 is 18 times 35. 360 is our 35th triangle number, and then the 12th Fibonacci, well, we just have to write them out. So 1, 1, 2, 3, 5, 8. What I'm doing is I'm adding the two previous terms, starting with a 1, 1, to get to the next one. 13, 21, 34, 55. Let's see how many we got. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 89, 11, and then 55 plus 89 is 144. All right, determine if the sequence converges or diverges. All we have to do is look at that R value. Is it less than or equal, or just actually has to be strictly less than 1? If it is, and we're talking about its absolute value, so I'll put the absolute value brackets here. It is less than 1, so this one converges. All right, is this less than 1? Yes, it is, so this one converges. This one here is the only one I see where the R value is greater than or equal to 1, so this one diverges. All right. Well, let's look at what's happening here. How do I get from 192 to 48? If I can't figure it out, I can divide the other direction. 48 divided by 192, and I get 0.25. So R here equals negative 0.25. That is less than 1, so this one converges. And this one here, 6.75 divided by 4.5 is 1.5. So this one diverges. All right, a couple more there for you to try. For 36, 37, the R value is kind of hidden, but we can find it. It's just the base. So this one converges, this one diverges, converges. Okay, now we're going to actually evaluate the geometric series. If you look at all of these R values, they are all less than 1, so all of these will converge. Now we just need to use the formula that these will converge to the series equals, I think it's a sub 1 over 1 minus r. Let me think. Yes. Okay. So let's plug this in. So 1 over 1 minus 3/4 becomes 1 over 1/4, which becomes a 4. Let's just see if we got a 4 for 40, and that will tell us if we're doing that formula right. Yeah, 40 is 4. All right, and so it's one of our simplest formulas for one of the more complicated scenarios. Just a sub 1 over 1 minus r. Let's try this one here. 1.9 over 1 minus a negative 0.6. 1.9 divided by 1.6 equals 1.1875. 1.1875. All right, but what if it's given like this? We got to figure out what that r value is. So I could do 1.66 divided by 8.3 to figure out what I'm multiplying by. This is a 0.2, so r is 0.2. So let's plug it into the formula. A sub 1 over 1 minus r. 8.3 divided by 0.8 is 10.375. All right, and that's exactly what we do for the rest of these. So try them, consult the answer key to make sure you're doing them right, and have a good rest of your day. That concludes this video.